Welcome back. This is the central lecture on the rate-based approach to corrosion. Once we start addressing the rates, we will also be directed to a topic called corrosion potential, and we will also connect to some of the topics which we have already discussed, like the Tafel slope. So the central challenge in the case of uniform corrosion is that the anodic region and the cathodic regions of corrosion cell are not separated via an electrolyte. So we discussed how these anodic corrosion reaction and the cathodic reaction can be visualized and operationally implemented via a cell like this, wherein this sample, which is getting corroded, is distinctly separated from a counter electrode. This not only helps us in measuring voltages and currents. From these voltages, we can plug these voltages into this equation and get to delta G. We can also impose external voltage source, external currents, and so on. So this transition to a distinct two electrode setup is very useful for understanding the behavior of a corrosion cell. With this, we could also look at which pairs of reactions are not prone to corrosion, and which pair of anodic and cathodic reaction may be prone to corrosion. Let's move on. Before we get into the central topic of this lecture, it is useful for you to revise this lecture that has been provided in this playlist. It is to do with electrochemical kinetics, and we looked at the kinetics of this particular reaction. So this single reaction has two aspects to it. There can be the reduction pathway, that is, this species, oxidized species, gets added via an electron, giving rise to a reduced species in solution. Corresponding to the reduction current and the oxidation current, there are two terms in the Butler-Warmer equation. We had interpreted the meaning of alpha and so on in this lecture. Please revise this lecture if you have not already done so. From this, we were able to get the overall current. So current density is plotted here. This is the oxidation current and reduction current, which are proportional to certain quantities. And from all these things, we define what is called the null potential. Null potential is the potential at which the modulus of the oxidation current and is equal to the modulus of the reduction current. So at null potential, the net current is 0. So this is an important quantity that would appear in many of these equations. And we also looked at the Tafel plot. You should notice how we are plotting the Tafel plot. From here, we could get the Tafel slopes, which are important indicators of a particular reaction. This is all presented in this lecture. Let's move on. What is different from this set of reaction to what we observe in corrosion? So here, what we are dealing with is a single reaction. Note that. I mean, it may have a reduction component and an oxidation component. However, we are still dealing with a single reaction. So that is what I'm emphasizing here. So current density is corresponding to the same reaction. There's a single reaction. In contrast to this, corrosion involves two different reactions. There is an oxidation, metal gets oxidized. This contributes to the anodic corrosion reaction. And there is a distinct reaction which is contributing to the cathodic part of the corrosion reaction. Okay, so this is one reaction. We here in corrosion we have pairs of reaction. This the central difference, and this has implications in the way we think about currents in a corrosion cell. Note the corrosion cell. In a corrosion cell, the anodic region is not separated from the cathodic region. So despite this issue, the electrochemistry can be well studied via this setup. In corrosion, current densities are unknown because the area relevant to the anodic part and the cathodic part is not very well defined. So we typically only deal with current as opposed to current densities. When we were quantifying the properties of this reaction, we looked at current densities. However, in corrosion, we are mostly discussing just current and not current densities because anodic and cathodic areas are unknown. From corrosion current, we can get to the rate of corrosion. It is also important to understand that there are other ways of getting to the rate of corrosion. We can look at weight loss of a sample. When a metal gets corroded and dissolves away, the weight of the sample, metal sample, decreases. So that is also a measure of corrosion rate. And it's also important to understand that the ohmic polarization is less significant in all corrosion studies. Okay, there are different ways to think about this. Ohmic polarization is associated with IR drop. So I is relatively small in corrosion, and R is also less due to some reason. For example, the electron transfer here is very facile, and the ion transport can also be facile because the anodic and cathodic regions can be near to each other. Because of all this, ohmic polarization is less. So these are some of the factors that make corrosion different from the study of electrochemical kinetics of this kind of reaction. So moving on. So with this reaction depicted in this manner, we will depict the currents of these two pairs in a slightly different manner. So corresponding to this reaction, there is this current given by the greenish yellow curve. Corresponding to cathodic reaction, there is this curve depicted in via the violet curve. Sum of these two curves is the green curve. So before we discuss these three quantities, let's first understand how did we get these curves. So these curves, that is the current versus potential curves in corrosion, is obtained via this kind of setup. So the advantage with this kind of setup is that you can get a good sense for what is the potential of the metal that is corroding, and via the imposition of external voltage, you can also drive external currents. Okay, so you can map the entire curve by changing the potential of the corroding sample and get to see how this curve evolves as a function of potential. Likewise, you can also get an understanding how the cathodic current gets modified as the potential changes. To understand why we have these three quantities, we have to look at the fundamental aspect of a corrosion cell. Before we go into this quantity called E core, core refers to corrosion. We will just reflect on what is the meaning of ENM. Okay, so this is null potential, which is not very different from the null potential considered in electrochemical kinetics. Okay, so if you are given a single reaction, okay, the single reaction can have an anodic part and a cathodic part, but given a particular reaction, there is a null potential associated with that. And given this reaction, there is a null potential associated with this reaction. That is straightforward and has the similar interpretation to any of the electrochemical reactions, which we have already considered in lectures on electrochemical kinetics. As opposed to this, these two quantities, E core is to be discussed here. First, let's understand and the important aspect of corrosion cell. So in a corrosion cell, there is an oxidizing reaction which generates electrons. And these electrons are the ones that are contributing to the reduction current. So at steady state, the rate of generation of electrons, that is the rate of or the anodic current, should match with the rate of consumption of electrons via a cathodic reaction. If this were not so, for example, when a metal starts corroding, it may be possible that the rate of anodic current is more than the rate of cathodic current. If that is the case, more electrons will be dumped into the metal sample, and the potential will shift in the metal sample so as to make the rate of generation of electrons from this reaction equal to the rate of consumption of electrons via the cathodic reaction. That is, the anodic current should match with the cathodic current if the potential of this metal is not going to be drift. So that potential at which the rate of generation of electrons here via the anodic reaction matches with the rate of consumption of electrons via a cathodic reaction, that potential is called E core. So this is the potential at which the net current is zero, and that is the potential relevant to corrosion of this metal. Moving on, as soon as you see this form of a curve, you would anticipate you can fit this curve to an equation of this form. So there is an exponential term, and there are few other terms. Here, this term is notionally the area of the corroding sample, okay? Because in we had mentioned that it is not possible to get the exact areas associated with the anodic reaction and the cathodic reaction in a corrosion cell, but we can get the area of the corroding sample at steady state. So this corresponds to that particular area. So using that term, you can also think through a corrosion current density, and this refers to the current that is represented via this particular term, this particular curve, and this term corresponds to the null potential. Likewise, the violet curve can be modeled or fitted to this particular equation, and you would have a null potential corresponding to the cathodic reaction of a corrosion cell. Once you have this form of an equation, you would tend to take logarithm and plot the exponential curve via a linear plot. So that is what is being shown here. So you take the log of partial current densities. What do I mean by partial current densities? There is current corresponding to the oxidation reaction and current corresponding to a reduction reaction. That's what I mean by partial current densities, or partial current, if not the current densities. All right. So um, most of the time we are just plotting the current and not the current densities. And you can plot the current uh, with respect to change in potentials, because the nature of the current changes as you cross the null potential. The slopes also gets modified. So because we have this exponential form, you can take a logarithm and represent the log of iox in terms of this component and this component. So that is what is being plotted here. So again, in these quantities, in this plot, three quantities are important: null potential, E corrosion, and null potential corresponding to the cathodic reaction. So E corrosion is the potential of the metallic sample which is getting corroded. At this potential, the rate of generation of electrons via an anodic reaction is equal to the rate of consumption of electrons via a single cathodic reaction, or the sum of cathodic reactions from multiple cathodic reactions. So what is important to understand is the significance of E core. This is the central quantity which will also give rise to I core. Okay, so once you know E core, E corrosion potential, from here we can get to I corrosion, which is the measure of rate of corrosion. Let's move on. So like we did in electrochemical kinetics, we can also get Tafel slopes in corrosion from this plot. So once we have these equations, we know how to represent these straight lines via these equations. From here, we can also get Tafel slopes. We do not want to be interpreting too much the meaning of alpha in this case, because in corrosion, most of these quantities are obtained via experimental measurements, and these are more or less like a fitting constant. They can be interpreted in more fundamental ways, but for now, let us just use these as fitting constants, and Tafel slope is something that is obtained via experiments. So Tafel slopes, referred via this symbol B, is the reciprocal slopes from these lines. So the slope of these lines correspond to this quantity and this quantity. And as you can see, the Tafel slope is the reciprocal of these slopes obtained from these Tafel plots. Just re-emphasize, E corrosion is obtained while the Tafel plots can be plotted by driving external current. E core is most significant in the absence of external current. So in the absence of external current, the rate of generation of electrons here has to match with the rate of consumption of electrons. So you have to connect, when you look at this curve, you have to connect to two particular aspects: how we obtain the entire plot, that is obtained by experimental measurements involving a 2-electrode setup or also a 3-electrode setup. I mean, rather a 3-electrode setup, because we want to get a measure of um, the potential of the corroding sample. But what I meant by a 2-electrode setup is that because we have an anodic region and a cathodic region here, which cannot be separated, we separate these two regions via an explicit 2 electrodes. And to get the potential of the corroding sample, we use the 3rd electrode, which is the reference electrode. So, and the second important aspect of corrosion is that at E-core, the rate of consumption generation here matches with the rate of consumption in this reaction. So let's move on. There is another kind of experimental measurement, which is often referred to as linear polarization technique. So what do we do? Here, this curve, okay, this dark green curve is obtained via a series of potential changes on either side of E-core. Okay, once this potential is established, or to get to this potential, you do a measurement corresponding to either side of E-core and get this green curve. Why is it called linear? Because very close to E-core, this curve, which is nonlinear, is expected to be linear. Okay, so because of this reason, it is called linear polarization techniques. So once you get this dark green curve experimentally by varying the potential in this region and measuring the current, you can also fit this green curve to a form as shown here. So this is the potential, which is the x-axis. E-core corresponds to this particular potential. So this form is fitted to a particular experimental data to get other terms shown here. So what is of significance are this pair of quantities. This quantity, which is the potential of the corroding sample at steady state, and I-core is the corrosion current, which is going to give you a measure of rate of corrosion. And another quantity which is often mentioned is the polarization resistance, because around this region, around E-core, at potential sufficiently close to E-core, you can have a linear behavior. We can also talk about polarization resistance. So this is given by this symbol R pole, polarization resistance, that is equal to 1 by slope at E-core, slope in this region, and the slope is di by dE. And why is this called a polarization resistance? Is because R POL, R polarization, is equal to dE by dI. So if the polarization resistance is high, we need a lot more change in potential to drive some changes in current. So this interpretation in terms of resistance makes sense, especially in areas close to E-core. Moving on, we would look at a closely related representation. There is no significant addition in terms of concept, just the representation is different, and this representation is called Evans diagram representation, and associated experiment measurements in the context of corrosion. In fact, we will not be introducing much new concepts in the next lecture, but just a representation which you would probably see in the corrosion literature will be discussed. We will look at this topic in the next lecture. Thank you.